Okay, let's get started, everyone. Welcome to the final session of PLDI 2026. You're in the static analysis and verification session. We have a set of four very interesting papers for the session, and we're going to start with our speaker, Gabriel Ebner. He's going to be telling us about PulseCore, a new system for verifying concurrent higher order programs.
Oh, thank you. So at Microsoft Research, there's a bit of an echo, sorry. We believe that proof-oriented programming with intrinsic proof works. I mean, like, to show this, over the years, we have developed about 1 million lines of code of verified star code that is deployed in various industrial applications. We have a cryptography that is deployed in Linux, in Python, in Firefox. We have verified parsers that are deployed in Windows, in Azure. Might be that like most people in this room have something running right now that is developed at Microsoft, written in F-star, and deployed in production. But we are running into limitations, and we want to expand beyond our successes. There are limitations to how we've been doing things. So we were using a system called Lodestar, which has a direct encoding of heaps, where you need to actually reason about heaps directly. And it also didn't have any concurrency, and its foundational model was more of a axiomatized effects in F-star style. And so if you look at the landscape of program verification these days, there is Iris, Iris, and Iris, and Iris is really amazing. But usually when people use Iris, they do a deep embedding of a proof of the program in Coq, and then do extrinsic proofs about that. But we want something that is intrinsic, that is in F-star, that where you interleave the proof with the program. And we also wanted to integrate with all the native effects in F-star. F-star has effects for ghost state, it has effects for divergence, and we want this to interoperate nicely. And to solve this problem, we have developed Pulse, a new separation logic that is written in F-star, and that does a lot of what Iris does, just in a smaller footprint, and integrated in F-star. So in particular, our foundation does not require any categorical machinery. There is no copies, no cameras, no ultramatic spaces, just what you can do in F-star. And roughly, the architecture looks pretty straightforward. So we're building on top of F-star, and not even full F-star, just a very basic total subset of F-star. There is none of the extremely sophisticated effects that we have available. So this is a foundation. The part of F-star we use is something you could do in any other proof assistant. You can do it in Lean, you can do it in Coq, you can probably even do it in Actor. And on top of that, we built a development of heaps, of atomic actions that operate on heaps, and then lift it into divergent computations. And on top of that, we have a new domain-specific language, Pulse, and using this domain-specific language, we have developed about 100,000 lines of code to evaluate this system. The existing F-star system is very useful because it already allows us to do the whole code extraction pipeline. We can extract to C, we can extract to Safe Rust, we can extract to OCaml, and that's what we actually make use of. So let's get started with some examples from the Pulse DSL. So if you recall the slide, the title slide, there was a word impredicative on it. And I'd like to just get enough separation logic that you can understand that single word. OK, so let me show you very quickly how Pulse looks like. So the key message here is Pulse is F-star plus mutability with separation logic-based ownership reasoning, a bit like linear types. And so if you have any dependently typed function that is already in pure F-star, you can directly use it from your Pulse program, even if it was not at all defined using Pulse. This is just the standard plus function in F-star. So you can use that in F-star with the dependent type. And then on top of this pure basis of F-star, we add mutable state. And for that, we get extra pre- and post conditions using separation logic. So these separation logic propositions, they encode resource ownership. So if you have a reference, you have a precondition that you own the reference and that the reference points to the value VR in this case. And then you just write your program with function calls that modify those resources that you have. And if you, for example, assign to your variable, then suddenly your resource changes to reflect the change in value. Now, in F star, in Pulse, we encode both the pre and post conditions, as well as what kind of function it is in the type. So on the previous slide, we saw like a regular function with side effect that is actually executed, but we also have ghost functions. Those correspond a bit, if you know Iris, to few shifts. And syntactically, those just differ by having a ghost keyword. And the story here is that these functions, they are only there for modeling. They are not they are not executed. They are erased. And all the ghost state, now a ghost function, what can it do? It can access a special part of the heap, that is the ghost heap, which only contains references that are not there at runtime, that are just there, for example, for bookkeeping when you want to verify concurrent programs. And all the ghost data we have in Pulse can be allocated and used just like regular references. You can allocate them, you can write to them, you can free them. And you can do this locally. You don't need to do any global setup whatsoever. And obviously, this is also defined for PCMs. So if you want to have some kind of complicated ghost state, monotonic state, you can define this in just the usual way. We even have like refined PCMs where you can give a subset of possible values for the memory representation. Another special kind of Pulse functions are atomic functions. So we don't extrinsically prove that functions are atomic. Instead, we have types that say, hey, this is an atomic function. And then the type checker verifies that essentially these functions only execute at most one atomic machine operation. And they look syntactically just like ghost functions, just like regular functions. And the type checker also allows you to run ghost functions inside an atomic function or after an atomic function, it is still atomic. Under the hood, this is all implemented using kind of monadic types. So there's a monad for atomic functions with a bind operation, and this surface syntax desugars into the monadic stuff. OK, now that we have these basic ingredients, let's get to like the core of the paper, invariants. OK, this is maybe a somewhat confusing topic, because the name kind of suggests that, hey, maybe this is like a loop invariant, but it's not. Maybe you think, OK, it's like an invariant on a binary tree. Also not. So the name invariant, I'm not sure who exactly introduced it, but it refers to something that is true at after every atomic step of your execution. And since we're in separation logic, it's not just true, but you also get ownership over it. Like the slogan that I want you to remember is that it is a named resource that you can temporarily borrow during one atomic operation, and then you have to give back. So it has nothing to do with loop invariants. It is an ownership construct. And it allows you to transfer resources between threads. And it's used to implement mutices, condition variables, any kind of concurrent data structure that you can think of. To give you a small example, let's look at how the invariant for a spin lock would look like. So here we've got this example. There's a predicate which is called if true then owns, and it is parameterized by a reference to a Boolean and a separation logic resource protected. So like that's just the SL prop, the heap predicate, and it's defined as there exists a value for this reference, and we own the reference, and if that value is true, then we also store the protected resource. And if we put this into an invariant, we then get two state transitions. If we have if the reference points to true, then the invariant also contains the protected resource. And if we acquire the spin lock, then the reference switches to false. And during this atomic switch, we can take out the protected, and afterwards, the invariant only owns the reference. So this is kind of like how these invariants look like. And the key thing that now I guess everybody has already discovered is that these invariants should be impredicative. And impredicative means that invariants can own invariants, that you can have an invariant inside an invariant. And previously, we saw that what this means is that, for example, the thing that is inside the lock can be, again, for example, another lock. So this captures the, so impredicative means that you can have locks that protect locks. You can have task pools that store tasks that refer to the task pool itself. You can also like have concurrent linked lists where each element in the linked list protects the ones that come afterwards. Okay, so it's really important that you can have this circularity in invariants. And generally speaking, with invariants, there are like two intricacies. One is that we need to make sure that invariants cannot be opened twice. I mean, usually you have some kind of invariant mask that tells you what you've already opened. And the other one is that this impredicativity requires some guards against unsoundness. If you put this in like naively, you get unsoundness in your system. And generally, you resolve this by adding step indexing in the later modality. We do this just like in Iris. And syntactically, the API for this looks very straightforward. In Pulse, we get a ghost function that turns any resource P into an invariant. We can duplicate it, this inf_i predicate, to send it to other threads. And if you want to use it, there is a nice surface structured control flow that allows you to open an invariant. And for the duration of this one atomic operation, you get the content of the invariant guarded by the so-called later modality. And this later modality and the associated later credits are an awesome invention from Iris, just from 3 years ago now. You can introduce this later modality using the later intro function. This is always possible, but to eliminate it, you require later credits. And the key trick here is that those later credits can be obtained outside of the atomic block. And since we're doing this intrinsic proof style, we can actually instrument the program so that you can obtain those credits at any point. And you don't see any kind of update modalities here, mainly because we can stuff those modalities into this later credit by function here. Okay, now this was a bit about how the Pulse DSL looks like. And now let's go to the implementation, about the theoretical foundations of it. So previously we were up there at the Pulse DSL, and let's now dive a bit into PulseCore. So in the Pulse heap type has 3 main components. One is the concrete heap, which models pretty much the physical memory. It's a map from physical addresses to stuff that is in memory. There's another field in that structure, which is the ghost heap. That one is erased. It does not appear at runtime. And then there is a higher order heap, which contains the invariants. It contains stored predicates, as well as the number of credits that are saved. And we found that those primitives are already enough to define most higher order state that you encounter in practice. I mean, there's some stuff that you cannot easily define using this. You cannot easily store, for example, heap predicate transformers. You can still encode them, but you cannot store them directly. Obviously, the big challenge here is how to define such a heap, because, again, the heap contains invariants, which contain heaps. And so generally speaking, this requires the solution of some kind of domain equation. Because the naive solution to this is, if you're just focusing here on the part where we store invariants, then you get that the heap needs to contain a map from addresses to heap predicates, and that is unsound for cardinality reasons. So now Iris solves this domain equation by defining a functor, an endo-bifunctor on a category of cophies, and then applies some sophisticated categorical machinery to construct a fixed point for this. But I'm very grateful for some anonymous reviewers of our previous version of this paper to point us to a much more simple and more elementary solution to this problem called indirection theory by Hober and Apple in 2010. And this, interesting enough, is the formal foundation of VST, of the VST verifier. And from what I understand, they moved away from VST to Iris because it didn't do invariants or any of these other cool modern features. But we managed to extend indirection theory with invariants and later credits, and to get a nice modern separation logic with impredicative invariants. And like what interaction theory gives you is a solution to this domain equation which introduces the levels by itself. So given so here, if you look at the second one, you get that the heap is kind of equivalent to the natural number, like a level, product, the address to heap predicate. And for any functor which turns a heap predicate into a heap, interaction theory gives you this kind of level stratified approximation. It's an approximation because the right to left map zero truncates the predicates to the current level. And this is really simple. It's like just 70 lines of F star, this core domain equation solver. Like maybe this diagram explains this a bit more. So like you get top level predicates that range over any heap. And then like the heap n contains predicates that only range over heaps that are strictly smaller. And the rest is just zero extended. And you can define this using just a well-founded recursion on the type in your favorite dependent type theory. Just define heap n is something something of heap m. Right. Yeah, and on top of that, we add these intrinsically typed actions. And those are, we are doing a shallow embedding. So these are really just pure F star functions that take one heap and give you back the output heap as well as the return value with some obvious side conditions that the input heap satisfies the precondition, an arbitrary frame, and the invariants. And there's, and the way we encode these later credits is simply by requiring that the level of the heap minus the stored credits is greater than 0 and decreases by at most 1. It's super straightforward. And ghost functions are just add one more extra condition, namely that they preserve the concrete heap. And this has then the effect that you can actually like turn an erased ghost action into a ghost action. So you can just store them as proofs. And on top of these actions, we now add a definitional interpreter to model divergence states. So we have a tree of actions, an infinite tree, and we write a field interpreter that gives semantic to this tree. And this definitional interpreter is correct by typing, and it's just a way to model semantics. The extraction is separate. OK, to conclude, the paper has 3 case studies. We have a task pool, a barriers, and a verified measured boot protocol. And there's lots of other stuff in Pulse. We got a core library, we got verified parsers, we got GPU kernels. And from here on, we're like looking to extend Pulse both on the theoretical side, doing prophecies, total correctness, and doing lots of implementation goodies, the new C front end, and just making it nicer to use. Thank you.
We have time for a couple of questions. Hi.
Ralph Jung, ETH Zurich. Thanks for the talk. Very nice to see Iris and F-star. I was wondering if you could say a bit about what you did on the resource side, like for the concrete PCMs that you own. Is it PCMs? Is it more like Iris's resource algebras? Are those the same because you just don't have a core? Like what are you doing on that front?
To be honest, I'm not fully clear on what resource algebras are in Iris. So in the heap in Pulse is really just a map from addresses to a type, a PCM on that type, and a value of that PCM.
Okay, and then like for the PCMs, do you have like some standard PCMs to keep reusing, or? Like
oh yes. So there. Okay. So like we've probably already seen like the most straightforward one, the ones that just allows you to write one value and then like with fractional permissions. You can use you can write your own PCMs, and then we have a library for various other PCMs like fancy constructions, anchored preorders.
Okay. Yeah, resource algebras are kind of a fun way to build more PCMs than if you just build them from smaller PCMs. Anyway, happy to talk later.
Oh yeah. I mean, like we can also do products. Yeah.
Yeah, sums work better. Anyway, we can talk later.
Okay. Yeah. Thanks.
Thanks.